Our last speaker of the morning is Francois Henn. He is a professor at the University of Montpellier, and he's going to talk about ions and water transport through micrometer-long single-walled carbon nanotube. So please, Francois, the stage is yours.
Hello, Mauro. Hello, everybody. I'm just going to make a try. If I put the full screen now, do you see the full screen, or do you also see the comment?
Screen, probably you have to put full screen the PowerPoint.
Is it a full screen right now for you?
I see your PowerPoint with all the PowerPoint tabs, not strictly full screen of the slide.
Okay. So I'm going to escape and okay. Let's go to okay. So I'm going to try to make it as large as possible.
I don't remember if here is I mean, a little bit better. I mean, if it is too complex full screen, I think that in this way it's still. Oh, okay. We are making improvement.
It's better now.
Okay. Sorry, Francois. Otherwise, you can press near the zoom on the left. There's a button. You just press the zoom button.
I don't know what is the zoom button. Where is it?
Go back to the zoom button at the bottom on the right.
Share, stop screen, or share screen?
No, in your presentation.
Back in my presentation. Yes.
Yeah, in your presentation. Okay, here it is. Press on it. No, the one you were on it before, on the left.
Yeah.
Okay, that's it. Yeah. Click on it.
Yeah. It's full screen now, or?
No.
Let's do the last try, and then we probably the other one on the right of the percentage.
Okay. Let's do it like that, or it's okay?
I think it's okay. It's quite large, so we can see. Sorry for interrupting you.
Okay, so hello to all, wherever you are in Roma or elsewhere in the world behind a computer. Not far from your bed, either because you're gonna go to bed soon or because you just get up. And so thank you to be present. I would like also to thank the organizer for giving us the opportunity to present the work of our research consortium, which bring together 3 French teams from the universities of Besançon, Montpellier, and Toulouse, and which is supported by our national research agency. Our objective is to study micro devices with nanofluidic system containing, if possible, only one single carbon nanotube, and which are single-wall carbon nanotube, separating 2 reservoirs that contains simple electrolyte like KCl, and which can also be submitted or not to an external electric field, which is perpendicular to the tube. We have built this consortium research group in order to be able to combine experimental and theoretical studies, either by means of analytical modeling or by means of numerical simulation of models for an all-atom system. So you are welcome to.
Just to be sure, are you changing slides or you are still at the first one?
Not yet. Not yet.
No, we were not sure of this. Sorry again for the interruption.
Okay, so and so you are welcome to visit our website for much more info about this research consortium. So many things have been already told by Alessandro a few minutes ago, because there is quite common feature with my talk. So we're gonna. So it's fixed, yes. So I really have to switch to the okay. It looks like I'm facing the same problem as the
Mm.
Alexandra, 1 hour ago, to go from one slide to the other, it doesn't move.
It doesn't move, or even with the page up, page down, or other.
Yes. Which page down, page up? Oh, okay. Is it okay now?
Yes, we see probably the second slide.
Okay. Sorry for the delay. So first of all, let's us recall the interest in studying carbon nanotubes as a nanochannel model. First of all, many of you probably know that we can play with very short diameters, so extreme high confinement conditions, and also with very long lengths for the nanotubes, so that the geometric ratio can be extremely high ratio with the surface, the smooth surface with low friction. We can also play with the accessibility by changing or maybe playing with the functional ends. It's an extremely thin layer of atoms, so can be extremely sensitive. The inside can be extremely sensitive to the outer environment, especially to water absorption or any other chemicals, or also electric fields. It's a flexible. When it's quite long, we can play and use the mechanical properties. So some works has already been carried out to look at the coupling between the vibration and the transport, and they can be semiconductors or metallic. So that may also play a role, an impact on the conductivity. So as I tried just with a few words to demonstrate that nanotubes, carbon nanotubes, is a unique artificial channel that can be very interesting to study ions and water at the nanoscale, but it also can be interesting and unique artificial channel for many potential applications, as nanofiltration, single molecule detection, energy harvesting, and what we could call now bio-ionoelectronics. Okay, so just as a proof, here is a non-exhaustive, of course, list of paper about this subject, because it's a growing subject, and just the paper which has been released the last couple of weeks. So dealing either with the ion and water, or just water confinements and motion inside this very strong confinement conditions. However, and despite this huge number of works and paper, yet there is no clear understanding of the physics which is behind this phenomena, and as seen so far, and that many points remain to be discussed. For instance, regarding the experimental issues, if we really wish to work on a single tube, then the data and the experimental results may depends on the different type of carbon nanotubes, depending on the method they are being grown, the geometry, the symmetry, the defect, and so on and so on. Of course, the diversity of the experimental device for the nanofluidics, the design, but also the number of tubes which are involved, the polymers that are used, the contact with the substrate, and so on, and the outside environments and the water, also depending on the electrolyte, the pH. And on the other side, on the other hand, from theoretical issues, there are many remaining open questions regarding the structure of water, the state of water at the absorbed surface, the impact of the curvature, the impact of the surface charge, and so on and so on. So many works has to be achieved still. As an example of the experimental issue is the disparity of the electrical behavior. Just here, I just show two examples that the behavior in terms of current voltage, it has been observed sometimes to be a ohmic or linear behavior, and what in other case which to be a voltage activated behavior, and which might be partly or fully due to the ion exclusion effect which is strongly dependent on the electrical charge on the nanotube wall, and themselves, which are highly dependent on the nanotube growth method and the environments of the nanotubes. There is also a disparity about the impact of the electrolyte concentration. It has been observed that at very low concentration, there is a power law, which is below than 1, but still, depending on the tube, the length, the diameter, and the different studies, the value of this exponent may vary and also depend on the pH. And it's also then when we take the whole set of conductance values reported in the literature are brought together, an extremely wide dispersion is also observed, as you can see on these figures. Again, this can be explained by the nature or the geometry of the nanotube and different experimental conditions. So it will nevertheless seem that beyond these differences, among which some can be well controlled, other factors that cannot control are responsible for these disparities. Modeling efforts, both using analytical and atomistic simulation, are thus necessary to get a deeper insight into the physics, which is then behind the conductance values and the quite peculiar behavior. So here we are proposing a general model taking into account two parameters which appear to be essential, the surface electrical charge density and the slip length. And Alessandro, in the previous talk, gave a lot of information about these two crucial parameters. As we propose to see if, by considering extreme values for these two parameters, it is possible to frame all the experimental results. First of all, the total conductance must be considered as the results of the resistance in series. One is associated to the entrance into the tube, and the second is the transport inside the tube. It can be thus demonstrated that in addition to the dimensional parameters, radius and length, the evolution of the conductance depends strongly on the ratio between the conductivity inside here, the pore, and the bulk. So just without giving too much details about the model, which can be found in a paper which was published by Ban and Hall in 2015 in Science Reports, let's simply note that the conductivity inside the tube is composed of several terms that modify the expected conductivity from the bulk by including the charge, electrical charge density at the surface, and the slip length. So now let's go back to this plot where we gather many experimental results, where the conductance is plotted as a function of length. So if we now use the model that I briefly presented, taking a radius of a carbon nanotube of 0.4 nanometers, a small one, but without any charge at the surface and without considering no slip length, here is the lowest values of G we can get. So you can see that most of the results are above. It's what's quite first interesting information. So we can plot the same in this condition without any charge and without slip for different radius. Finally, we can take now into account the values of the maximum values for the slip length and for the charge. We come from the literature, and it's come from different studies. Not that it has been shown, moreover, in many studies that from molecular dynamics, but also from the Alessandro work, that there is a strong correlation between the slip length and the surface increase. Indeed, surfaces with a high charge density are more hydrophilic, whereas high slip length is associated to hydrophobic nature of the surface. Therefore, combining the most extreme value for the slip length, which is here taken as 1.4 micrometers and 0.21 coulomb per square meters, we even push the extreme limit of the model for the calculation of the conductance as a function of the length. So what can be seen on this figure is that, there are most of the data are included in the frame, but some of them show higher values, which are much higher, because just let me recall you that we are in a log scale in that scale. So one can therefore question the validity of either such data or the parameters considered in the model. However, noting that most of the data fit well with the minimum and maximum values expected by the model, we are rather inclined to question the experimental results. So this model that whatever the question is, that the model presented is a phenomenological and does not explain the origin of the surface charge and the friction at the surface of the nanotubes. So this question raised at the beginning of this presentation, the question remain extremely relevant. What is the origin and impact of the surface charge, the impact of the grafted groups at the surface or at the entrance of the tube, the impact of cavitation or depletion, the impact of electric field, and the coupled impact of mechanical and electrical fact and stimuli. So here we just show from molecular simulation how we try to bring some insight into at least the question regarding the surface charge electric field combined to electric field, and the question arising from the impact of the group graft at the entrance or at the surface. So here from its simulation, molecular simulation using quantum mechanics, and which showed some water molecule confined in a tube to which a perpendicular electric field, a strong electric field, is applied. So when there is only water inside the tube, there is no splitting of the protons and the hydroxide OH minus. But when there is only one, even though in the presence of salt like chloride, sodium chloride, it can be seen that the protons is attached and interact strongly with the surface and polarizing the tubes, and then due to this polarization in the second step, then the hydroxide group can be absorbed. So that might be explained to some extent the effect, of course, of voltage, especially if we consider that a local scale, we can the tube can experience extremely high electric field. The other and the last example is the effect of the chemical groups graphed at the surface at the entrance of the. So that was achieved using molecular dynamics. So the main information which can be retrieved from this calculation is that when quite high density of carboxyl groups are attached at the entrance, grafted at the entrance of the tube, then first of all, what we observe is that the voltage activated current, which was already expected from a very simple model that we published a few years ago, that assuming that there is a potential barrier at the entrance that may explain this non-ohmic behavior. And the other very interesting information here is that even at low voltage, of course, the higher the concentration, the higher is the conductivity. But due to the absorption of the cations at the entrance, there is a kind of blocking effect, meaning that when voltage is higher, then the conductivity of the higher concentration is lower than the lower concentration. Okay, so I think my time is over now. So I would like to thank my colleagues from these UNESCO project groups. the colleagues from the University of Montpellier and myself, we are more devoted to work on the experimental fabrication of the device and the electronic and ionic conductivity measurements. My colleague also from Montpellier and Toulouse, we are co-workers for the analytical modeling. And last but not least, my co-workers from Besançon, who are performing the computing simulation and whole atom, whether it is quantums or classical field simulation. Okay, so thank you for your attention, and I would be now pleased to back to questions.
Thank you very, very much for your talk. I have a couple of questions. In one of the last sketch of simulation that you show about water absorbance, it seems that there is some deformation of the core, at least visually. I was wondering if this deformation can be compared with some experiments, because I mean, there can be issue maybe in the carbon field, in the simulation, something like that.
I cannot hear you.
Oh, can you hear me now?
Yes. So I could not hear the after a few words, the beginning of your question.
The idea is that I see that there are some deformation in your carbon nanotube in one of your last slides. And I was wondering if there is any possibility to compare experiment and simulation to see if this deformation is something, I mean, for which simulation are reliable or not.
First of all, the time scale is extremely short. Its deformation are vibrational deformation, which are quite well known. The mode are well known from nanotubes. Okay, but here you have to remind that maybe to see this effect, we had to apply the extremely strong electric field. So what might not be exactly, I would say, realistic. It could be maybe at very local scale. So, in the simulation, the length of the tube is as large as the diameter, because we could not make simulation with too many atoms. So it might not necessarily be representative of the real deformation of a micro long deformation of the nanotube. Yeah.
Thank you. I also have quite last general question, and then maybe if people have other questions can use the chat. In one of your initial slides, if I correctly understood, you discussed the fact that the current voltage curve is non-linear, and in particular at high voltage there is an increase in the current that is non-linear. And I was wondering if there is any theory, I don't know, based on free energy, I mean, whatever, that is able to catch this behavior.
Yes, we publish our colleagues from the analytical modeling just show that if you input in your very simple model, in your model of series resistance, a potential barrier, it could be at the entrance of the tubes or even at the middle because of heterogeneity due to the change in the electrical charge at the surface or maybe to any other environmental or even defect. And if you produce a potential barrier inside the tube or at the entrance of the tube, then you can recover and show that you get non-ohmic or voltage activated behavior. Okay.
Thank you very much, Francois, and thank you also to Alessandro and Alexandra for their interesting talk. And then that's it for the morning in Italy, and see you in the afternoon for the other section.